Yeah, and I'm not sure if we are going to get the answer for this question, but there will be the general answer how to solve this kind of problems.
So thank you, and by the way, thanks for switching session chairs with me, because otherwise I would chair my own talk, which is not a problem. But so this is work with Yoni, and it's part of our program in analyzing combination properties, which is, our mascot is the unicorn. So SMT, I'm not going to give too many details here, because I'm assuming that everyone here at least knows what I'm talking about. So we want to answer whether a quantifier-free formula in a theory with equality first order. These are restrictions that not everyone agrees upon. I mean, there are works trying to generalize many of these properties in several directions, but I'm assuming quantifier-free formula, first order theory with equality, and so on and so on. And this is a very general structure that you would like to answer whether unsatisfiable or satisfiable, possibly with a proof or a model. So one important part of SMT is combining theories, because, I mean, if you have a decision procedure for this theory and for this other theory, and you have a problem that mixes the two, it would be useful to have a decision procedure for the combination of them. And I mean the combination in a very obvious way, let's say. So if you have a theory of numbers and you have a theory of arrays, you can have a theory of arrays of numbers by combining the two. So the problem is combining theories is very difficult in general, meaning that you can start with two decidable theories and end up with an undecidable one, and not to mention the complexities involved that can grow when you combine. And so there are a lot of methods in the literature. I list some of them here, but there are many more. And usually a combination method is something of the following form. So if one theory is decidable and has some property, and a second theory is also decidable and has some other property, their signatures are disjoint. Of course, there are people working on non-disjoint theories, but this is more difficult. And then the combination of them is decidable. The proof of this usually offers you an algorithm that combines the both algorithms you started with. So now, this work is a little bit of a fever dream. It's a very strange thing, but we decided it deserved to be known. So bear with me. What is the natural density of a set of numbers? Is this limit that tells you more or less which fraction of the natural numbers a certain set occupies. This is not always well defined. So we worry mostly about sets where this is defined. And well, what is the spectrum of a theory? I mean, here in a one-sorted setting, if you have worked with descriptive set theory, this is not the usual definition, but is the one that works for us. So is the set of numbers that corresponds to, so the spectrum of T relative to a formula phi is the set of cardinalities of models of T that satisfy phi. And here we are restricting to natural numbers plus F0, so countable numbers because we have Lowenheim-Skolem and we are assuming the signature is at most countable because that's usually the case in theory combination. And just a reference, a number is computable when you can generate fractions that that converge to it. So let's just give one example. Consider this theory, which is used often when providing counterexamples in theory combination. Essentially, you have no symbols except for equality, of course, and the models have cardinality either even or infinite. Then the density of this theory, which is the density, I think I failed to mention. So you define the density of a theory relative to a formula as the density of the spectrum, and the density of a theory is the density of the theory relative to a tautology. So essentially is the density of the set of all cardinalities of models of T. For T even, this is easy. It's half. Half of the numbers, half of the natural numbers correspond to a model of this theory. Now, there are more complex examples. So take the Chaitin constant for the Busy-Beaver numbers, is this number here. It's non-computable. It's you can't approximate it after some threshold. It's an awful number, really. But you can still find a theory that has this density. So we take no symbols for now, and models of size 1 through 5, 11 through 52. This is because we are approximating the decimal expansion of omega, and 100 through 521, and so on and so on. And the density of this weird, very weird theory is the Chaitin constant. So it's not trivial. The densities can be some wild numbers, really. So now the question, the obvious question, why do we bother mixing number theory with probabilities and theory combination? Well, I find it interesting. To me, this is enough reason, but there are other reasons as well. The fact is, Yoni and I and Benjamin have been working on a program. Benjamin is talking later in the second SMT session. We are working on a program of understanding the interplay between combination methods and the limitations of these combination methods. And one very important part of this program is generating counterexamples. So, of course, this serves as some basic tools that you can look at a theory and say, okay, I can see that the density of this theory should be some number, and I know from these properties that this implies this theory can be combined with a certain method. But most importantly, these results help us create these counterexamples. At least for me, they are very useful when constructing these counterexamples. And I mean, we had some very interesting results. In this paper, we proved that theory combination assuming only politeness is impossible, and this kind of result I'm going to talk about helped us with that. And later, Benjamin is going to talk about this paper, which has also counterexamples that, at least for me, these intuitions that I will show here help with finding. So Combination methods. Let's go. So, as I mentioned before, we have a general structure for a combination method. For now, I'm going to focus on one sort. This work was mostly one-sorted, but we also considered any one-sorted signature. But for the presentation, I'm going to focus on empty signature because things are a bit easier then. So I think a lot of people have heard of Nelson Open. Nelson Open involves a property called stable infiniteness. Is the same property that is required for both theories. And it means that a quantifier-free satisfiable formula phi has to have an infinite model. Essentially that. So, like if one theory has a spectrum that looks like this, or even a theory relative to a formula has a spectrum that looks like this, and the other has a spectrum that looks like this, then we can combine the two because we have infinite in both spectrums. And it's easy to see by compactness that if the density of a theory is greater than 0, then you can combine it using Nelson and Open. This is very easy. This is not one of the difficult proofs in the paper. I mean, if you have density greater than 0, this means that you have elements arbitrarily large. And then, of course, by the compactness theorem, you have to have an infinite number in the spectrum as well. So this is very natural. Okay, then we have shininess, which for decidable theories is equivalent to strong politeness, which you can find in CBC5. Essentially, the spectrum is the interval from min mod to infinite, where min mod is a computable function that returns a finite element, which is the smallest element in the spectrum of phi. The spectrum will look something like this. So you have from 5 to infinity, all elements included. And of course, if the theory is shiny, then the density is 1. This is quite clear, but it's more useful to think, well, if the density is not 1, then the theory cannot be shiny. So this is useful when searching for counterexamples. Now, another method is gentleness. Again, the two properties coincide. For shininess, the amazing thing is that you only need what properties for one theory. The other theory can be anything, as long as it's decidable, of course. Gentleness, you require that both theories are gentle, which means it's not a very natural property as a stable infiniteness. But it's natural enough. It means that the spectrum of every formula is either finite and computable or co-finite and its complement is computable. And I mean computable in a very strong sense. You need to be able to output this set and know when you finished outputting this set. It's not, so we call this usually strong computability. But it's usually enough to think of just the set is computable. So the spectrum of a gentle theory can look like this. So you have only finitely many elements that are not here. Or it can also look like something like this, where you have only finitely many elements in the spectrum. And of course, in the first case, we have the density is 1, and in the second case, we have that the density is 0. Easy enough. And these are the main combination methods that we consider. So far, I would say the paper is not that interesting or not that challenging, but in the middle, we considered some other properties. So part of the definition of shininess is that there is a function min mod that is computable and returns the minimum element of the spectrum. This is very important for more than one combination method. We have shininess, and in a paper we published recently, we have used the computability of the minimum model function to to have a new combination method that is a bit different from shininess. And well, one theorem that I think exists somewhere in the literature, I've heard whispers and rumors about this, but I couldn't find a reference, sadly, but it's easy, it's not too difficult to prove that a theory has computable minimal model function if and only if its spectrum is a computable set. And then, if a theory has a computable minimal model function, then the density is a computable number. In addition, every computable number is the density of a theory with a computable minimal model function. Usually we use this in the converse. If the density is not a computable number, then the theory cannot have a computable model function. The construction involves this crazy staircase function, which depends on a sequence that converges to the density you want, to the non-computable function, the computable number that you want. And amazingly, it uses medians, also known as Ferry sums, which are this kind of addition, which, you know, it's wrong, but it works. So it's enough for me. And so in our example using Chaitin's constant, I have no idea of how to prove this in practice, but I know that this theory doesn't have a computable minimal model function because its density is a non-computable number. So it's helpful. Now, finite witnessability is a very involved notion that it includes a function witness that is computable, takes a quantifier-free formula and returns another quantifier-free formula, and it satisfies two conditions about having enough variables in a way and about being somewhat equivalent to the formula you started with. It's defined for the combination method called politeness, but as I mentioned before, we recently proved that this is not actually a combination method. So why do we bother thinking about witnesses? It's because witnesses are an important part of the strongly polite theory combination method, which works, and it's used in CBC5. So this is an important step in the direction of having strong politeness. And the amazing thing, which was unexpected, is that every number is the density of a finitely witnessable theory. I was planning to explain this graph, but I see I don't have that much time, and this is a really weird construction, so I'm going to skip it for now. And now comes a very interesting result as well. We are talking about density, and one of the most important results in number theory in the last 50 years, I believe, is Semeredi's theorem that proved a conjecture by Erdos and Turan that a set that has positive density has arbitrarily large, long sequences in arithmetic progression. Very weird result, but if you change this for computable subsequence instead of arithmetic subsequence, then this is false. It's a very difficult result construction. And these sets are studied in descriptive set theory a lot. They are called immune sets. But we were able to prove a similar result to Semered's theorem that if a sequence thought as a set has positive density, then you can bound it by a computable sequence. This implies that if the density is greater than 0, then the theory is finitely witnessable. And now what I want you to think is that, okay, we proved a similar result to Semered's theorem, so it should be just as hard. Well, it is not. This is a red herring. The proof is not easy, but it won't mean a Fields Medal for us for discovering it. It's a shame. So, conclusion and future work. I think that actually this is the most important result of the paper. So we were able to generalize our classification now for gentleness as well, and at least for the one-sorted case. And not only that, we showed that these are the possible natural densities. And these are exactly the possible natural densities for theories satisfying these properties. So for every number in these sets, you can find a theory, a corresponding theory. This is the set of computable numbers. What is next? Other combination methods, there are others that we haven't considered. Alternative densities. Dirichlet's density is interesting to consider because we can play with the Riemann's gamma function. There is the logarithmic that is the same as Dirichlet if you use as weight the entire set of natural numbers, but you can use other weights, which I have no idea of what that would imply, but sounds interesting to me. We have Schnirelmann's density, and this is a result that didn't end up in the paper, but that I love, that T gentle implies that Schnirelmann's density of the theory is a rational number. So we have computable numbers, we have rational numbers, it's all fun. And many sorted theories are a bit more difficult because then you have a plethora of possible densities for a set in n dimensions. And I guess that's it. Thank you for listening to this, again, fever dream. But yeah, it's very nice. Thanks for the organizers and so on, so on.
Thank you.